There was a time when satellites did nothing more than observe. They orbited quietly, programmed to follow a schedule, obey commands from Earth-based operators, and send back whatever they happened to see. But something has changed. Today, satellites are learning to make their own choices, which regions deserve attention, and even how to filter out useless data before it ever reaches human eyes. They no longer just look, and as strange as this sounds, they think. They become autonomous decision makers, evolving, adjusting, and operating at 27 times the speed of sound. We've crossed a threshold where Earth's orbit is no longer filled with silent metal machines, but with digital minds that can scan, assess, and adapt in real time. Artificial intelligence has slipped into orbit, and it's quietly rewriting the rules of surveillance, exploration, and space warfare. The sky hasn't changed, but the brains behind it have. The result is a world under the lens of machines that learn, decide, and evolve without human permission. This is the moment AI took over the skies, and we barely noticed. But behind that quiet shift was a deeper revolution. Not in hardware, but in how satellites were trained to think. Let's go back to where this all began. The dream of smarter spacecraft didn't start in Earth's orbit. It began deep in the deserts of Mars, and in the quiet hum of machines that were never meant to wait for orders. Back in the 2000s, NASA engineers were already asking bold questions. Could a machine make decisions alone, millions of miles from Earth, without waiting for a signal that would take minutes or hours to arrive? The answer came in the form of code. Starting with Curiosity's ability to independently fire its lasers at targets and continuing with Perseverance's use of onboard AI to decide which Martian rocks were worth analyzing. NASA's rovers were the first to demonstrate that space machines could begin acting on their own intelligence, not just following instructions, but making judgment calls. These were systems designed to interpret their environment, adapt to hazards, and operate with the precision of human scientists, but without the delay. But that was just the beginning. Fast forward to now, and the same logic has reached orbit. NASA's dynamic targeting system, for instance, does not just take photos. It scans cloud cover up to 300 miles ahead, processes the data on board, and makes a call in under 90 seconds on whether to act. This is what autonomy looks like. Satellites that skip useless shots, save storage, and zero in on real events like wildfires, rare storms, even volcanic eruptions without anyone prompting them. We're not just programming them anymore, but training them. And that training is scaling fast, not just in Earth orbit, but across the solar system. Gone are the days when satellites were passive observers, waiting for Earth-bound operators to decide what to photograph and when. Thanks to the emergence of AI-driven autonomy, these spacecraft are learning how to observe, decide, and act all within seconds and without ever phoning home. NASA's Jet Propulsion Laboratory has already proven this with its dynamic targeting system, where a satellite can look 300 miles ahead of its own orbital path, recognize clouds that would obscure ground-level data, and autonomously cancel those shots in favor of clearer terrain, all in under 90 seconds. This system was tested aboard CubeSat Cognusat 6, a briefcase-sized satellite carrying an AI processor designed by Ubotica. In low Earth orbit, this AI doesn't just follow pre-programmed instructions, it actively assesses whether it's worth taking a picture. If clouds block the view, it saves the data space. If the coast is clear, it locks on and fires. And soon, the same AI won't just avoid weather, it will hunt for it. New algorithms are already in place to target wildfires, volcanic eruptions, and severe storms before ground teams even know they've begun. The U.S. Space Force is automating satellite positioning, maintenance prediction, and anomaly detection. And over in Europe, the ESA is using machine learning to manage entire satellite constellations, reducing human workload and increasing efficiency across the board. We're not just programming satellites anymore, we're letting them think, which means the sky isn't just full of eyes, it's full of minds. But what happens when these thinking machines stop just watching the Earth and start learning from it in real time? For decades, satellites acted like flying cameras, snapping everything in sight, then dumping raw data down to Earth, where analysts sifted through oceans of noise to find meaning. But in the era of onboard AI, that entire process is reversing. The intelligence doesn't wait on the ground anymore, it lives inside the satellite. Take ESA's PhiSat-2, for example, a nano-satellite no bigger than a cereal box. It doesn't just photograph Earth's surface, it interprets what it sees. 6 onboard applications can detect cloud formations, flag marine anomalies, recognize wildfires, and even categorize changes in ecosystems, all before a single bite reaches Earth. Simply put, PhiSat-2 is far from being just a data collector. It is an analyst in orbit. And it's not alone. IBM's PAIRS Geoscope combines AI, satellite imagery, weather forecasts, and ground data into powerful visual analytics used in forestry, utilities, and agriculture. Meanwhile, EOS Data Analytics, launched by Max Polyakov, uses its own AI-augmented satellite, the EOSat-1, to deliver hyper-targeted insight into soil degradation, crop health, and even early-stage pest outbreaks at scale in real time. And thanks to machine learning, satellites are no longer static reporters. They're adaptive observers. Algorithms now decide what to capture, ignore, and escalate, all while flying at 17,000 miles per hour. This shift saves bandwidth, time, money, and human effort. And in places like NASA's sensor web, satellites are working together with ground sensors to automatically flag high-temperature zones, trigger alerts, and redirect orbital assets for closer looks without any human typing a command. One AI spots a volcano awakening, another satellite pivots to catch the plume before it fades, and an entire constellation now moves with shared intelligence. But the real breakthrough isn't just that satellites can think, it's that they're starting to anticipate things. AI has transformed Earth observation from reactive snapshots into proactive forecasting, giving us a glimpse of the future through algorithms trained on millions of square kilometers of planetary change. It starts in agriculture, where AI-powered satellite constellations like EOSDA don't just monitor crops, they forecast yields, flag soil degradation, and detect drought stress weeks before it becomes visible. With multispectral vision and pattern recognition, satellites can now see a food crisis before the plants even wither. In the atmosphere, NASA's dynamic targeting takes forecasting to the next level. Flying on board the Cognasat-6 CubeSat, it looks ahead on its orbital path, detects cloud patterns, and autonomously redirects sensors for clearer, more useful imagery, all in under 90 seconds. Future tests will allow the same AI to spot wildfires and rare storms as they begin, tracking them real-time from above, not just documenting their aftermath. Meanwhile, MIT's game theory-driven traffic models use reinforcement learning to teach satellites how to avoid orbital collisions before they happen, essentially predicting the future behavior of debris and rerouting accordingly. And deep learning tools are being used to detect subtle temperature shifts in satellite hardware, forecasting malfunctions before they cause catastrophic mission failure. Prediction isn't limited to the planet either. NASA's ExoMiner system recently sifted through 14 years of Kepler Space Telescope data to identify 300 new exoplanets, planets no human or machine had previously found. Trained on past discoveries, it recognizes the signature patterns of distant worlds light years away, buried in data noise too vast for the human eye. AI's predictive power means we're no longer simply cataloging reality, we're anticipating it. We're seeing the future unfold at the speed of orbit. And if prediction is power, then the next logical step is action. Satellites that don't just see or guess, but react. We've passed the threshold where satellites simply serve as eyes in the sky. Now they act on what they see, thinking in orbit, without waiting for ground control. At the center of this transformation is onboard autonomy. Spacecraft no longer rely solely on human commands to make decisions. NASA's Aspen system, for instance, plans and adjusts spacecraft operations using intelligent scheduling algorithms. It detects system anomalies, reroutes mission priorities, and even initiates corrective action without human oversight. On CubeSats like Cognasat-6, we're seeing real-time image analysis become mission-critical. Trained AI algorithms now assess incoming visuals mid-flight. If clouds block a target, the system cancels the capture, pivots, and saves resources for a clearer opportunity. Decisions made in seconds, entirely in orbit. In manufacturing, AI is hands-on. It's now embedded in space defense operations. The U.S. Space Force uses onboard AI to track rogue satellites and rapidly shifting threats. Algorithms flag deviations in orbital behavior, triggering alerts or initiating avoidance maneuvers, giving operators a strategic edge. This is a paradigm shift, from passive machines waiting for orders to active agents shaping the outcome of their missions. It reduces the delay between problem and response, which is crucial in environments where every second matters, and a few seconds can mean disaster. And we're just scratching the surface. With the rise of federated systems, one satellite's onboard analysis could soon redirect the actions of an entire constellation in real time, forming a thinking, adapting network above our heads. But even intelligence in motion needs a brain to manage it all, an operating system for the skies. And that's exactly what's coming next. One intelligent satellite is impressive, but dozens, operating in synchrony, Communicating, learning, and adapting as one system, now that is creating a new kind of intelligence in orbit. This is the future of satellite constellations, not just clusters of hardware circling Earth, but coordinated systems guided by AI. Think of it like a swarm, where each satellite isn't just a node, but part of a shared brain. NASA's research into federated autonomous systems is laying the groundwork. In this model, each satellite performs its own onboard analysis, then shares that insight with the next. If one unit detects a wildfire, a trailing satellite can redirect its sensors to zoom in, adjust exposure, and confirm the observation, all without human instruction. This is already being prototyped. The Federated Autonomous Measurement Project aims to deploy this type of shared targeting across constellations, where AI makes collective decisions based on constantly updated observations. SpaceX has also begun implementing limited autonomy across its Starlink network. In crowded orbits, self-coordination becomes not just efficient, it's necessary for survival. This level of coordination demands immense processing power and real-time adaptability. AI isn't just helping satellites react, it's teaching them to anticipate. From weather anomalies to shifts in radio frequency environments, constellations that think can update their objectives and redistribute workloads on the fly. This kind of operational fluidity, which was previously impossible due to time delays between ground and space, is unlocking new models for Earth science, climate monitoring, and even space traffic control. These smart constellations blur the line between satellite and sensor network, between machine and system. We are no longer managing dozens of separate missions, we're enabling one integrated mission with dozens of autonomous limbs, each learning from the other. But as AI reshapes how satellites think and work together, one question looms larger than ever. Who controls the system when it starts making decisions faster than we can? Space has always been a one-way conversation. Commands went up, data came down. Control centers issued every directive, and satellites followed blindly. But now, artificial intelligence is changing the chain of command. NASA's dynamic targeting system was one of the first big breaks. Onboard algorithms now decide, in real time, whether an image is worth taking or if a better opportunity lies ahead. That judgment, once made by teams on Earth, now happens in under 90 seconds, thousands of miles above us. In this new paradigm, the operator becomes more of a partner than a commander. Human input still guides the overall mission objectives, but AI executes them, adjusts on the fly, and in some cases, overrides redundant instructions to optimize results. This shift raises the stakes. If an autonomous system decides what to see, what to ignore, and when to act, where does accountability land when something goes wrong? Military applications already grapple with this. The US Space Force and European agencies now test satellite systems that autonomously detect threats, adjust positions, and even initiate countermeasures. AI is becoming not just a tool, but a gatekeeper of decision-making in orbit. And it's not just about what AI does, it's about what it hides. These systems filter data before it reaches Earth. In doing so, they prioritize certain signals over others. That makes them powerful, but it also makes them opaque. Who decides and audits what the AI prioritizes? We're entering an era where the autonomy of machines isn't science fiction, but autonomy without oversight is a recipe for blind trust. And in space, trust is a dangerous luxury. So as satellites begin to take their own calls, humanity must ask, are we still steering the mission, or are we simply passengers in a system too complex to control? AI in space isn't standing still. The systems we see today, those that detect clouds, reroute around storms, or adjust their missions in real time, are just the beginning. What's coming next isn't a reaction, it's a prediction. With reinforcement learning and neural networks, satellites are now being trained not to just see the present, but to anticipate the future. These aren't just tools of observation, they are agents of foresight. Platforms like IBM's PAIRS Geoscope and EOS Data Analytics already allow satellites to forecast droughts, predict crop yields, and detect early signs of natural disasters from orbit. But the real leap is in collaboration. Researchers at MIT, working with aerospace partners, are developing systems that allow entire satellite constellations to think and act as a swarm, sharing intelligence, making distributed decisions, and dynamically aligning roles without waiting for instructions from Earth. In this new space order, a single event like a methane plume or a wildfire can trigger a chain reaction. Dozens of satellites shift formation, realign sensors, and respond as a unit, all powered by machine logic that improves with every orbit. Even the hardware is adapting. Modular satellites are now designed to receive AI upgrades post-launch, allowing their brains to evolve without a recall to Earth. That means your weather satellite in 2025 could become your deforestation monitor in 2028, with no physical change, just smarter code. We built satellites to be our eyes in the sky, but in teaching them to think, we may have built something more, an ecosystem of intelligent machines quietly learning, evolving, and deciding how to best observe, and maybe even protect, the planet that built them. If you made it this far, thank you for sticking with us. There is more where this came from. Just subscribe to Project Aerospace and turn on notifications to stay in the loop.